Welcome to the video lecture on product and quotient rules in higher order derivatives. In previous video lectures, we've talked about some basic derivative rules, things like the derivative of a constant is zero, the derivative of a power rule, the derivative of a constant times a function. What we haven't looked at so far is how to take the derivative of two functions being multiplied together or two functions being divided, and this is called the product and the quotient rules. So let's start with the product rule. Suppose that we have two functions, f and g of x, that are differentiable functions, and we want the derivative of the product of those two functions. So what would make sense, what would be easy, would be to just take the derivative of each individual function and multiply the results together. So one good guess for what the product rule should be is that you would take the derivative of the first function f, so we could write that as df dx. Then we could take the derivative of the g function, we could write that as dg dx, and then just multiply the two results together. Now, I'm not claiming that that's what the product rule is yet. Let's see if this works. So it would make sense that it should work because the derivative of a sum is the sum of the derivatives. So let's see if the derivative of a product equals the product of the derivatives. So let's take a very basic product of two functions. Let's look at x squared times x to the fifth. So the x squared is kind of like our first function f, and the x to the fifth is like our second function g. So if we were going to apply our guess of a rule here, then we might assume that the derivative of this product should be the derivative of the first function, and the derivative of x squared using our product rule, using our power rule, would be to bring down the power 2 and subtract 1 from the power, so the new power would become x to the first. If we take the derivative of our second function, x to the fifth, using that power rule, we would bring down the 5 and then subtract 1 from the power, which would make this 5x to the fourth. And then according to our guess up here, we should be able to just multiply those two derivatives together to get our final answer. So 2 times 5 is 10, and x times x to the fourth is x to the fifth. So this is kind of what our guess would be. Now let's find out what the derivative actually is. So one way to figure out what the derivative actually is to go ahead and simplify this product before we even begin. And we can do that by our laws of exponents, which we know are true. So x to the second times x to the fifth, when you add those powers together, is really the same as x to the seventh. So that we know is true, and we also know what the derivative of x to the seventh is by a known rule, our power rule, which we've already proven, and that becomes 7x to the sixth when you bring down the power and subtract 1 from the exponent. So here's what the actual answer is. So let's compare. Does our guess match the actual answer? Obviously not. So unfortunately, our assumption that you can just take the first function and take its derivative and multiply that by the derivative of the second function doesn't quite work out so nicely. So what we're going to do next is prove what this derivative of a product turns out to be. And the only way that we can prove it is to fall back on our limit definition of the derivative. If you don't know what a derivative is and you don't have any nice shortcut rules for it, you always have to go back to your definition. So the limit definition of a derivative says the limit as delta x goes to 0 of our function evaluated at x plus delta x minus our function evaluated at x divided by delta x. So we have to find that limit. And in this particular problem, what we're trying to do is we're trying to find the limit, or the derivative of this product. So when I say f times g of x plus delta x, that really means the f evaluated at x plus delta x times the g evaluated at x plus delta x. And then we're going to subtract from that the f evaluated at x times the g evaluated at x. So this is what our limit definition of the derivative would look like for the product of f times g. Now, in order to make this limit doable and usable, we're going to have to do something kind of unexpected, and this is probably not something you would just think of doing on your own without someone telling you what to do. So here's sort of the trick that we're going to use. What I'm going to do is I'm going to leave this f of x plus delta x times g of x plus delta x right where it is in the front. And then what I'm going to do is I'm going to add in and subtract in the same quantity inside of this numerator. So I'm really just adding and subtracting the same amount, which means I'm really just adding in a 0. So I'm not changing the equivalence of my problem. I'm keeping it equal to the step before this, but I'm going to change it in a way so that it's hopefully more useful to me. So here's what I'm going to do. I'm going to actually start by subtracting f of x plus delta x times g of x, and then I'm going to add in that same exact expression, f of x plus delta x times g of x, and then that minus f of x g of x that we had up here, I'm going to keep that on the end. So the stuff that's in blue adds to 0. So it's like taking an equation and adding and subtracting 2 from both sides. You're really not changing the equation because you've just added 0. So I haven't changed this limit, but hopefully by what I've added and subtracted in, I can now rearrange some things and make this a little bit more user-friendly. So let's see why this is going to help me. If I take a look at the first two terms, this term here and this term here, what do they both have in common? They both have an f of x plus delta x. So what I'm going to do just from those first two terms is factor out that f of x plus delta x, and then in parentheses what would be left over would be this g of x plus delta x minus this g of x. And then if I look at these two last terms on the end, they both have a g of x. So I am going to factor out a g of x, a positive g of x, and in parentheses that means I would be left with an f of x plus delta x minus this f of x. Now one more thing that I'm going to do, I'm going to split up this great big fraction which has a denominator of delta x, and I'm going to split it up into two fractions. Since they both have the same denominator, again, this statement right here is exactly equivalent to this statement before it. It's just like saying 2 plus 3 over 4 is the same as 2/4 plus 3/4. That's all I did, is I split this up into two separate fractions. Now, look at the individual fractions. We want the limit of this whole term plus this whole term. So the limit of a sum is the sum of the limits. So I am going to take the limit of this first piece. So I'm just recopying this whole first fraction, and then I'm going to take the limit of this second piece. Now if you look at what's in my parentheses right here, the limit of that is exactly the limit definition of the derivative of g. Because if I asked you to find or use the limit definition of g, you would say, well, the derivative of g is defined to be the limit as delta x goes to 0 of g of x plus delta x minus g of x all over delta x. So the limit of this piece right here is actually going to turn into g prime of x when I take the derivative. Similarly, this piece right here, when I take the limit of it as delta x goes to 0, that is exactly the definition of the derivative of f. That's the limit definition of the derivative of f. So this turns into f prime of x. Now let's go back to what was left over. In front of this derivative of f, we had that g of x, which isn't a function of delta x at all. So it's acting like a constant times a function. So this g of x will still be there in the limit. and these two things are being multiplied together. Then we have addition in front of that. Over here, this f of x plus delta x does have a delta x in it, but as delta x goes to 0, this part goes to 0, so in the limit, this goes to f of just x. And again, there's a multiplication in between those two things. So here is what we've just come up with. The derivative of a product of f and g is the first function f times the derivative of g plus the second function g times the derivative of f. So here's the formal definition of the product rule. We have the derivative of f times g is the first function f times the derivative of the second plus the second function g times the derivative of the first. So there is addition involved in the product rule. And you do take the derivative of f and you do take the derivative of g, but you're doing them separately and multiplying them by the other function unchanged. So this f doesn't have anything done to it times g prime, and this g doesn't have anything done to it, but it's being multiplied by f prime. Okay, so this is our product rule. It's a lot more complicated than you would have expected, and it doesn't really fit what our common sense would tell us should happen. So it's a rule that you are going to have to memorize. Now we will practice this in just a few minutes, but I want to show you a couple more rules here before we start practicing. So we're going to take this product rule, which is the product of two different functions, and I'm just going to show you how this would expand into the derivative of three different functions. So suppose you wanted the derivative of f times g times h. Now you could prove this doing the same kind of proof that we did up here for our limit definition of the product. I'm not going to go through all of those steps. You could probably find that in your textbook, but what the end result is very similar to our product rule for two functions. It looks like this. Our derivative of f times g times h turns out to be the first function f times the second function g times the derivative of the third function plus the first function f times the derivative of the second function g times h plus the derivative of f times g times h. So you can see that I took the derivative of each individual function exactly once. Here's h prime, here's g prime, here's f prime. And each time I do that derivative, I multiply it times the other two functions unchanged. So again, it's very similar to our product rule for two functions. Just make sure that you take the derivative of each function once and correspondingly multiply it by the other two, or however many you have, and add all those pieces together. Alright, so there's our product rule. Let's talk about the quotient rule, and then we'll start practicing. Now the quotient rule is exactly like the product rule in that it's a much more complicated rule than you would expect, and it is not very easy to memorize, it's not very easy to use, and it doesn't really fit what our common sense would tell us. So suppose I wanted the derivative with respect to x of the quotient of a function f on top divided by a function g on the bottom. So here's what the quotient rule says. You take the bottom function g times the derivative of the top function f minus the top function f times the derivative of the bottom function g all over the bottom function g squared. And notice on that bottom we're not doing a derivative of g, it's just whatever g was originally, quantity squared. So as you can see, this is a pretty complicated rule. So there's a little saying that goes along with this to help you remember how the quotient rule works. I learned this when I was in high school taking calculus. So here's how I think about it. If you have your function f on top, I'm going to think of that as my high function because it's on the top, it's above. And I'm going to think of my function g that's on the bottom as low. So I have my high and my low. So according to this derivative for the quotient rule, you would take your low function g times the derivative of the high function, so d high, minus the high function f times the derivative of the low function g, so d low, over the low function squared, or low times low, low, low. So here's how the quotient rule works using this little saying. It's low d high minus high d low over low, low. Low d high minus high d low over low, low. Okay, so feel free to use that if you want to help you memorize how this quotient rule works. Make note that the order on the top does matter because it is subtraction. So you always want to start with the low, or the bottom function g first, times the derivative of the top, minus the top times the derivative of the bottom. And this expression in the numerator is exactly a product rule, except you have subtraction instead of addition. Okay, so it's very similar to that product rule. All right, we've learned a couple of rules. Now let's put them into practice. So suppose we want the derivative of this product. We have x squared minus 2x plus 1. That's going to be our first function. And then we have x cubed minus 1. That's going to be our second function. So our product rule says to take the first function, so this derivative will be the first function times the derivative of the second function plus the second function times the derivative of the first function. And because this one is addition, which one of these you do first doesn't matter. You could do the derivative of the first times the second plus the derivative of the second times the first. You could switch the order around, and that's okay because it's plus. I'm just going to stick with how I wrote it earlier for my product rule. So here's how the product rule would be applied. I'm going to take my first function, all of this, and I'm going to recopy it unchanged and leave it wrapped in parentheses. So there's my first function. And then I'm going to multiply that by the derivative of this second function. Now the derivative of x cubed is a power rule. So you bring down the 3 and you subtract 1 from the power. And the derivative of minus 1 goes to 0 because that's a constant. So the derivative of the second is the 3x squared, and then our first is this x squared minus 2x plus 1. So now we've done the first half of our product rule. Now we have to add to that the second function, just recopy it unchanged, times the derivative of our first function. And again, this is just a polynomial, so I'm going to use my power rules. The derivative of x squared, the 2 comes down, and when I subtract 1 from the power, it becomes just 2x, minus the derivative of 2x. The 2 stays there because it's a constant multiplier, and the derivative of x goes to 1. So this is just a minus 2, and then the plus 1 goes to 0 because it's a constant. So the derivative of the first is 2x minus 2, and the second function is that x cubed minus 1. Now, usually we're going to be doing stuff with this derivative, so it's usually a good idea to go ahead and simplify this. So I'm going to have to go ahead and do some distributing. 3x squared times x squared is 3x to the 4th. 3x squared times minus 2x is minus 6x cubed. 3x squared times 1 is 3x squared. And then over here I'm going to have to FOIL. X cubed times 2x is 2x to the 4th. Then I get a minus 2x cubed, a minus 2x, and then a plus 2. And then combining like terms, I have a 3x to the 4th and a 2x to the 4th, which is 5x to the 4th. A minus 6 and a minus 2 is a minus 8x cubed. Then I have a 3x squared by itself, and then a minus 2x plus 2 by itself. So here's my final derivative, all cleaned up. Okay? All right, let's look at this example. Now this is obviously a quotient because we have that big division bar. So this is going to be my high, and this is going to be my low, and it's going to be low d high minus high d low over low low. So the derivative of this quotient will be the low function recopied unchanged, and wrap it in parentheses when you do that. So the low is that x squared minus 1. Then I need to multiply that by d high, the derivative of this numerator, which again is just a polynomial, so I'm going to be using power rules. The derivative of the x cubed becomes 3x squared plus the derivative of 3x, well, the 3 stays there and the x goes to 1, and then the derivative of the plus 2 goes to 0 because it's a constant. So there's my low d high. Now I need to subtract from that high d low. So the high is this cubic polynomial, wrap it in parentheses, and then we're going to multiply that by the derivative of the bottom, d low. So the derivative of x squared is 2x, and the derivative of the minus 1 goes to 0. And then I'm going to divide all of that by low low, which is just that bottom function, either multiplied by itself or that's the same thing as squaring it. So the low low is really the bottom squared. Okay, notice I didn't take a derivative in the bottom. I only used my derivatives on the top. Now, again, this is probably something you would want to clean up. So let's go ahead and distribute. I'm going to get a 3x to the 4th. Remember to FOIL here. And then I'm going to get a positive 3x squared, and then a minus 3x squared, and then a minus 3. And then over here, when I distribute my 2x, I might as well take the negative with it. So what I'm really going to do here is I'm going to change this minus to a plus and stick that negative in front of my 2x term and distribute the negative with the 2x. So this becomes a minus 2x to the 4th, a minus 6x squared, and a minus 4x. Now it's only in the numerator where I really need to FOIL out, because that's where potentially some like terms could combine or cancel out. In the denominator, there is no need to FOIL. Leave it in this factored form, this quantity squared, and don't bother trying to expand that. It's only the numerator that you need to worry about simplifying. In this numerator, it looks like our 3x squareds are going to cancel. I have a 3x to the 4th minus a 2x to the 4th, which is just x to the 4th. And then I'll have that minus 6x squared still there. I'll still have my minus 4x still there, and I have my minus 3. So there's what my numerator looks like, and here's sort of my cleaned up derivative. Okay? All right, the next example. We have cube root of x times parentheses square root of x plus 3. So this is like a product rule again, because we have a function out front here being multiplied by this whole quantity. So this is sort of your first function here, and this is your second function here. So we need to use our product rule on that. Now before I do that, think about what it's going to require. In order to do the product rule, you need the first function times the derivative of the second plus the second function times the derivative of the first. Now the derivative of the first and the second involves some radicals, and what we know from previous lectures is that we don't really have a good rule for how to take the derivative of those immediately without first changing them into something like a power rule. So what I would recommend here is changing that cube root of x to a rational exponent, and a cube root is the same as a 1/3 power. Similarly, a square root of x is like an x to the 1/2. So change those so that now this is your first and this is your second. So our first function would be x to the 1/3. We're not doing anything to that first function, but what we're going to do next is multiply it by the derivative of the second function. So in parentheses, that would be the derivative of an x to the 1/2. You bring the 1/2 down, and when you subtract 1/2 minus 1, when you subtract 1 from this power, 1/2 minus 1 is a negative 1/2. So the new power will be negative 1/2. And the 3 goes to 0. So there's my first times derivative of the second. Now I want to add to that my second, which is that x to the 1/2 plus 3 that I had originally. And then I want to multiply it by the derivative of x to the 1/3. So I bring down my power, and this time when we subtract 1 from the power, 1/3 minus 1 is like 1/3 minus 3/3, so that becomes a negative 2/3. So the new power will be negative 2/3. Now to clean it up, if I multiply these two guys together, I'm going to pull that 1/2, which is my coefficient out front, and then we would have to multiply these two x terms. Now they have the same base, so laws of exponents say that I should be able to add their powers. So a 1/3 power plus a negative 1/2. You need a common denominator there. 1/3 is 2/6, and 1/2 is 3/6, and I really am subtracting these because of that minus. So 2/6 minus 3/6 is negative 1/6. Now over here, I'm going to distribute this 1/3 x to the negative 2/3 across to both of these. So again, when I do x to the 1/2 times 1/3 x to the negative 2/3, I'm going to pull that 1/3 out front, and then I'm going to get my two x's combined by adding these two exponents. So a 1/2 plus a negative 2/3. Again, I need a common denominator. So 1/2 is the same as 3/6. And if I change 2/3 into a denominator of 6, I would have to multiply by 2. So this would become a minus 4/6. And 3/6 minus 4/6 is negative 1/6. And then finally, 3 times 1/3 cancels out to a 1. So this is just going to be 1 times x to the negative 2/3. Finally, notice that 1/2 x to the negative 1/6 and 1/3 x to the negative 1/6 are actually like terms because they share the same variable and same exponent. So 1/2 plus 1/3 would be 3/6 plus 2/6, or 5/6. So this is going to be 5/6 x to the 1/6 plus x to the negative 2/3. So it's a bit messy with all these fractions, but there is our final derivative using that product rule. Now, just as a side note, if you notice something here from this original expression, original function that we had, there would be a way of doing this, and maybe what would be considered a slightly easier way that would avoid this product rule altogether. So an easier way to do this problem would be to take our function g of x, which was that x to the 1/3, that cube root of x, times that square root of x, or x to the 1/2 plus 3, and to go ahead and distribute that x to the 1/3 across before you even start taking derivatives. So x to the 1/3 times x to the 1/2, when I add 1/3 plus 1/2, we get that 5/6. And then if I distribute my x to the 1/3 times 3, that becomes 3x to the 1/3. And now if I go and take my derivative, I don't need a product rule at all because this just becomes a bunch of power rules. So the derivative of x to the 5/6, we're allowed to bring that 5/6 down, and when you subtract 1 from that, 5/6 minus 6/6 becomes negative 1/6. And when when I go to my 3x to the 1/3 and I bring that 1/3 down, 3 times 1/3 cancels out, so the coefficient would just be 1. And when I subtract 1 from my power, 1/3 minus 3/3 is negative 2/3. So comparing our two solutions over here, and I noticed that I forgot to bring down my negative, I had just a little typo right there, then you can see that these two answers are actually identical. And it was much simpler to do it this way, using just the distributive property first and avoiding that product rule altogether with all the simplifying that had to go into getting this final answer. So one thing that I always recommend to students is if there is an easier way to find your derivative that avoids using the product rule or the quotient rule, then I usually encourage you to do it in an alternative way because it'll save you a lot of time. Okay? So let's see if we can use that on this next example. So this one is kind of complicated because we actually have a product of two functions on top together with a quotient. So what we're going to try and do is avoid trying to use both the product rule and the quotient rule simultaneously, because that can get pretty complicated. So a shortcut here would be to easily eliminate that product on top by just distributing this x across. So my function on the top just becomes x cubed minus x over x plus 3. And now at least I don't have to do a product rule, I just have to do a quotient rule. And at this point, in what we've learned so far, there's no other way to avoid using that quotient rule. So we're going to have to just dig our heels in and go for it. Remember, this is our high, and this is our low. So the derivative will be, you always start with the low first. So we're going to do low d high. So low would be x plus 3. D high, or the derivative of the top, would be 3x squared. And the derivative of x just goes to 1, but we have that minus sign in front. So the d high is 3x squared minus 1. So we have low d high minus high d low. So the high is the x cubed minus x, and the d low, well, the derivative of x is 1, and the derivative of 3 goes to 0. So the d low is just 1. All over low low, or the bottom squared. And if we clean this up a little bit, we do have some foiling to do on the top. We're going to get a 3x cubed minus x plus 9x squared minus 3. And I don't have to do anything with this 1 because that'll just keep the x cubed minus x the same, but I do have to distribute my negative. So I will get a minus x cubed plus an x. Remember, you don't need to bother foiling out the denominator, just the numerator, because that's where the terms are going to combine or simplify. So 3x cubed minus an x cubed is 2x cubed. We get a minus x and a plus x canceling out, and we have that plus 9x squared, and then we have that minus 3 on the bottom, or on the end. So we have our final answer right here. Okay? Now, in the next several examples, I'm going to show you some alternative ways to avoid having to use this messy quotient rule whenever possible. So this won't always be an option, but in several problems, usually you can avoid the quotient rule. So if we look at this first one right here, how could we avoid using that quotient rule? Well, we could just use some laws of exponents to try and simplify this function first so that it's no longer a quotient. And we can do that because these x's share the same base. So our laws of exponents say that when you're dividing these two x's, you just subtract the two powers. So 3 halves minus 1, or 3 halves minus 2 halves, is just a half. So this becomes that 4 sticks around, and 3 halves minus 1 is an x to the positive 1/2. So this function is really just 4x to the 1/2. And I know how to take the derivative of that very easily. You leave the 4 where it is, because it's a constant multiplier, but you bring down that 1/2 power, and when you subtract 1 from the power, 1/2 minus 1 gives you a negative 1/2. So simplifying, 4 times a half is 2. And if you want, this is just an option, you could stop here, or you could flip that x to the 1/2 down, or you could even turn that x to the 1/2 into a square root. All of these 3 options are correct. Okay? Now, if you look at the next example, let's try something somewhat similar. We're going to try and change this quotient into something without a quotient in it. Now, the first thing that we can do is we can realize that this 4 over 5 is really just a coefficient of 4/5. So that's a constant out front. Now, the x squared, unfortunately, is in the bottom, but we know how to flip that up into the numerator because that's what a negative exponent does. So an x squared in the denominator is really an x to the negative 2 in the numerator. So we've changed this into just a power rule again. So using my rules, the 4/5 will stay there because it's a constant multiplier, and the derivative of x to the negative 2, we bring down the negative 2, and when I subtract 1 from the power, it becomes a minus 3. Simplifying, 4/5 times negative 2 is negative 8/5, and since it was written without negative exponents to begin with, I usually use that as a clue that I would want to write my final answer without negative exponents as well. So I'm just going to take that x cubed and push it into the denominator next to that 5. So here's what my final answer would look like. So if we look at this next example, again, it looks like a great big quotient, but we get a little bit lucky here because that denominator is a single term, or what's called a monomial. So what we can do is we can break up this big fraction by dividing that monomial into each of the two terms in the numerator. So this becomes 2x cubed over 7 minus x over 7. We're just splitting up this single fraction into two individual fractions that share the same denominator. So they're still equivalent. Now by doing that, we can now rewrite each of these terms because this coefficient out front is just a 2/7 and that x cubed is off to the side. And there's an implied 1 in front of that x. So the coefficient here would be like a -1/7 with that x off to the side. So f prime of x now would be the derivative of this. I haven't done any derivatives yet, but now I can by just using my power rule and my constant multiplier rule. When we bring this power down, it gets multiplied by that 2/7, which is going to turn it into a 6/7, and the power on the x goes down by 1, so this is now going to be an x squared. And then on the second term over here, the 1/7 will stay there because it's a constant multiplier, and the derivative of x goes to 1. So my derivative, without having to use a product rule at all or a quotient rule at all, is just 6/7 x squared minus 1/7. Now on this last example, we could do this just like we did this number 6 by moving that x to the 8th up to the top and changing this into 3x to the -8, and therefore the derivative would be -24x to the -9. Very simple, easy way to do it. What I want to show you over here is instead of just doing that power rule to get that answer, I do want to show you how the quotient rule would still apply to this, just so you can see the difference between the amount of work that would have to be done. So let's apply our quotient rule to 3 over x to the 8th. So we want to do low d high minus high d low over low low. So low would be x to the 8th. Now d high, the derivative of 3 goes to just 0. So this d high is just a 0. So there's low d high. Now I want to subtract high, which was 3, times d low. And the derivative of x to the 8th would be 8x to the 7th. You subtract 1 from the power. And all of that is getting divided by the bottom squared, low low. So x to the 8 squared. Now when we go to simplify this, 0 times x to the 8th, that's just going to be 0. So the numerator will be -24x to the 7th over x to the 8th squared. That's a power to a power, so you multiply these two powers. So 8 times 2 would be 16. And then we can use our laws of exponents again to subtract these two powers. I'm going to leave the -24 on the top, and I'm going to put my answer in the denominator and make that exponent positive because 16 is bigger than 7. So 16 minus 7 should be a 9, but because the bigger power was in the bottom, that's where my answer should go. So that's exactly what we would have gotten if we had just moved that x up to the top to begin with and used our power rule. But it's a little bit more work. So no matter how you do it, you'll get the right answer, but you can save yourself a lot of time and energy by using some of these shortcuts. Now this power rule that we've been talking about, I just want to mention that this power rule does apply no matter what kind of power you have. It can be any integer, positive or negative. It can be any real number as well, fractions, decimals, and so forth. So the power rule works for any kind of power n. Now that we know this quotient rule, we can develop our derivative rules for our other 4 trigonometric functions. Now hopefully you remember from a previous lecture that the derivative of the sine function is just cosine, and the derivative of the cosine function turns out to be minus sine function. So we're going to use those two pieces of information plus our quotient rule to help us figure out the derivative of tangent, secant, cotangent, and cosecant. So let's start with the derivative of tangent. Now notice this notation. This big D is like a derivative operator. So this means take the derivative with respect to that little variable x of the function tangent of x. So this is really the same as the derivative with respect to x of tangent x. Now in order to do that, we don't know what the derivative of tangent is, so either you use your limit definition, which is a pain, or you use a little trick. And the trick I'm going to use is that tangent is the same as sine x over cosine x. It's a quotient of two functions that we already know a little bit about. So we're going to apply the quotient rule to this new expression. So this is my high and this is my low. So the derivative according to the quotient rule should be low d high minus high d low over low low. So low would be cosine. D high, the derivative of sine, is also cosine. So there's low d high minus high d low. The high is the sine of x, and the derivative of low, the derivative of cosine, is minus sine x over low low, the bottom squared. Now when we go to simplify this, what you'll notice is cosine x times cosine x is cosine squared x. And I'm just going to put that little 2 in between the cos and the x just as a little shorthand notation, but that means the same thing as cosine of x quantity squared. Similarly, a minus times a minus becomes plus, and sine x times sine x is sine squared x. And on the bottom, again, using that shorthand notation, this is just a cosine squared x. Now let's use a little bit of our identities. Hopefully you notice on the top there that we have a cosine squared x plus a sine squared x. And based on our unit definition of our trig functions, they form a right triangle using a hypotenuse of 1, and so it's known from one of our Pythagorean identities that cosine squared x plus sine squared x, that's always 1. So one of our identities tells us that that numerator just becomes a 1. And another identity that we have is 1 over cosine is the same as secant, because secant is the reciprocal of cosine. So 1 over cosine squared will just be secant squared. So the derivative of tangent turns out to be secant squared x. Okay? So if we take a look at the derivative of secant x next, let's derive that. We're going to do something similar. We're going to change secant of x into its reciprocal function 1 over cosine x. And then I'm going to apply my quotient rule to that quotient. So my high is the 1 and my low is the cosine. So the quotient rule would say low d high. So the low is the cosine. The d high, well, the derivative of 1 goes to 0. So there's low d high minus high d low. High is just 1 times d low, the derivative of cosine is minus sine, over low low, the bottom squared. So when we go to simplify this, 0 times cosine just goes away, and a minus times a minus becomes a positive sine of x on top. And then what I'm going to do with that cosine squared is, instead of just putting that square inside and making my shortcut notation, I'm going to actually break this up and do cosine times cosine. And the first cosine I'm going to think of as being underneath that sine x. And we know that sine x divided by cosine of x is tangent of x. The second cosine is also in the denominator, so it's going to be under like a 1, a factor of 1. And 1 over cosine x is also known as secant of x. So the derivative of secant x is tan x times secant x, or usually in textbooks they have it in the other order, which it doesn't matter because multiplication is commutative. So the derivative of secant is secant times tan. Okay? So we've just derived the derivative of tangent and found that it's secant squared, and we've just found the derivative of secant is secant times tangent. All right, let's try something similar here. Using the same proofs, I'm not going to go through it all because I think you can manage to do that on your own. You could rewrite cotangent as cosine over sine and then apply the quotient rule to that. And by using the quotient rule together with a few identities, you'll see a very similar proof to what we did up here for tangent, but this time instead of getting secant squared for your answer, you'll get cosecant squared and you'll also get a negative. So derivative of cotangent of x is negative cosecant squared x. And again, a very similar proof for cosecant's derivative. You could rewrite it as 1 over sine x and then use the quotient rule on that together with maybe a few identities, and you'll have a very similar proof like we did for secant, but instead of getting secant times tan, you'll get cosecant times cotan, and you'll also get that negative out front. So the cotan function and the cosecant function are the ones with the negatives. Okay? So these 4 different derivative rules are things you have to memorize. You will be expected to know them by heart without any formula sheets on a test or quiz. Okay? So let's practice. Let's find the derivative of secant x divided by x. Now, you can do this any number of ways. You can leave it like this and apply a quotient rule. If you really detested the quotient rule, you could move that x up to the top and make it like an x to the negative 1, and then multiply that by that secant x, and then you could use a product rule. So that's an option as well. I'm just going to stick with the quotient rule because I don't want to get involved in all these negative exponents. So I'm just going to apply the quotient rule. The same final answer should turn out no matter which rule you use. So the quotient rule on this would be low d high. So the low is the x, and the derivative of secant x, we just found that out, was secant x times tangent x. So derivative of secant is secant tan. So there's low d high minus high, which is that secant, times d low. The derivative of x just goes to 1 over low, the bottom square. So just rewriting this a little bit neater without the parentheses, this becomes x secant x tan x minus secant x all over x squared. And you can't really reduce that because you can't factor out an x from the top to reduce anything with the bottom. So you're pretty much stuck. If you really wanted to, you could factor out a secant x from the top, but it's not going to help you cancel with anything in the denominator, so it's not really necessary. So here's my final answer. Okay? So let's look at number 10. Here we have x cosecant x plus cotangent x. Now this is important because this x cosecant x is often overlooked by students. This is really x times cosecant x, which means you have to use a product rule on just that first piece of this sum. So we do need to apply a product rule to x cosecant x. So to find this derivative, if I use the x as my first function and the cosecant x as my second function, then the product rule would say the first function x times the derivative of the second function. And remember, the derivative of cosecant is cosecant cotangent, but there's also that negative out front. So there's first times derivative of the second plus the second, which is my cosecant, times the derivative of the first, and the derivative of x just goes to 1. Now I'm not quite done. That's just the product rule on this first term. We need to add to that still the derivative of this second piece, because the derivative of a sum is the sum of the derivatives. So what's the derivative of cotangent of x? Well, that's cosecant squared of x, but with a minus sign out front. So let's distribute and clean up a little bit if we can. Can't really do much with this first product right here, except I'm going to take that negative and pull it out front of my x. So this becomes minus x cosecant x cotangent x, and then cosecant times 1 is just going to stay cosecant, and then I have a minus cosecant squared x. If you really wanted to, you could factor out a cosecant, but again, none of these are like terms, nothing's going to cancel out, so that's just an option if you really wanted to. Alright, next example. Here we have our quotient again. Now there's options here. If you stick with the quotient rule, then you can just jump right in. The other option is to notice that this is the same as 1 over sine x, doing this, and a minus cosine x over sine x. And 1 over sine x we know is cosecant, and we know cosine over sine is cotangent. So if you rewrote this, then the derivative here would just be the derivative of each of these two pieces. And the derivative of cosecant of x is that cosecant cotangent with the minus out front. And then we have our subtraction, and the derivative of cotangent is cosecant squared with that negative. So we get a minus minus, which becomes a plus. So our final answer is negative cosecant cotan x plus cosecant squared x. Now that's how I'm going to do this one, but there's certainly nothing wrong with doing a quotient rule on this original function and doing your low d high minus high d low over low low. But I will bet that your final answer is going to look a little different than what I got, because your final answer is probably still going to be in terms of sines and cosines. Now if you did a little bit of work to rearrange it, you could make that answer look the same as mine. Both answers are correct, and it doesn't matter which way you do it. But just be aware that sometimes how you approach a problem can affect how your final answer is going to look, especially if you're trying to check your answer versus the back of the book, for example. Alright, next example here you can see is exactly what we just did. So cosecant x minus cotangent of x, that's exactly this function just rewritten. So we found it out by doing the derivative of cosecant, which is cosecant cotan with a minus sign, and the derivative of cotangent would be cosecant squared with that minus sign. So you get that minus minus. So here's the final answer for this one. Now if you had done your quotient rule on this particular example, then you would have gotten a much different looking example, or different looking answer. So just to show you what that would look like, you would have low, which is sine of x, times d high. The derivative of 1 goes to 0. Then you'd have that minus there, and the derivative of cosine goes to minus sine. So you actually get a minus minus, which is a plus. And then you would subtract from that. That was your low d high, so now we need high d low, and the derivative of sine is just cosine. All over low low. So in the numerator here, we would get sine times sine, which is sine squared x. And in the top, when I distribute the negative and the cosine, negative times 1 times cosine x is minus cosine x. And a minus times a minus becomes plus. Cosine times cosine is cosine squared x. Now one thing you should recognize again, and we've seen this in a previous example, is that sine squared plus cosine squared is 1. That's one of those identities. So we would get 1, and we still have that minus cosine x on top over sine x quantity squared. So this is probably where you would have stopped if you were doing it with a quotient rule. But what I want to point out is if you split this up into two separate fractions, this guy and this guy, you'd have 1 over sine of x squared minus cosine of x over sine of x squared. And 1 over sine is cosecant, and when I have that square in there, 1 over sine squared becomes cosecant squared. And for the second fraction, you can think of this as a cosine over, and split up that sine on the bottom into two different fractions. So one of the signs goes under the cosine, and that becomes a cotangent, and the other sign goes underneath a 1, and that becomes a cosecant. So notice what we got is exactly the same answer that we did using this other method. So there's lots of different options here with these product and quotient rules, just depending on how you approach the problem. And they're all correct. It's just a matter of what you choose to do. Okay, the next example says find the equation of the tangent line to the graph of f of x equals tangent of x at the point pi over 4, 1. So first thing you have to remember is if you want the equation of a tangent line, the first thing you need to find is the slope of the tangent line. Because you can't find an equation of a line without knowing its slope. And a slope of a tangent line is exactly the same as a derivative. So we need to know what f prime of x is going to be. Well, if our function is tangent of x, then the derivative of tangent of x, we've already proven, is secant squared of x. Now that's your derivative function anywhere. We need the derivative at this particular point. So we need to find out what this derivative is when x is this pi over 4 right here. So let's plug in pi over 4 for x. Now this is going to require recalling your unit circle a little bit. If you prefer to know your cosines and sines, and maybe you're not so familiar with your secants and so forth, you could rewrite this. Secant is 1 over cosine, so secant squared would be 1 over cosine squared of pi over 4. And hopefully you remember that cosine of pi over 4 is root 2 over 2, and we want that squared because we want cosine squared. So this becomes 1 over 2/4, which becomes 4/2 when you use the reciprocal, which is just 2. So my slope m is 2. And I know my point, I know the x was pi over 4, and they also told me the y was 1. So I know a point, and I know a slope, so I can use point slope form. So that's going to be y minus the y coordinate 1 equals my slope m times x minus my x coordinate pi over 4. So we get y minus 1 equals 2x minus 2 times pi over 4 reduces to pi over 2. And then I'm going to go ahead and add that 1 over to the other side. I can't really combine these because I have that pi in there, so I'm just going to push that plus 1 off to the side. So this is the equation of my tangent line. Okay, so you find your derivative first, then plug in the x value of the point you're looking at, and then use point slope form. Now, one very common type of question that you're going to be expected to know how to do is to find where horizontal tangent lines occur. So think about that for a moment. If you want a horizontal tangent line, you should know that horizontal lines have what kind of slope? They have 0 slope because they're horizontal. So a horizontal tangent line means that the slope, also known as the derivative, needs to be 0. So we are looking for where this slope, where this derivative is going to hit 0. So that requires finding f prime of x and setting it to 0. So let's find f prime of x first. And this is going to require using that quotient rule. So we're going to do low, which is x squared plus 1, times d high, the derivative of x squared is 2x, minus high, which is that x squared, times d low. The derivative of x squared is 2x. The derivative of the 1 goes to 0. All over low, low. So that bottom squared. Now here we definitely want to clean this up because we are trying to do something with this derivative. We're going to eventually set it to 0. So let me distribute my 2x across. I'll get a 2x cubed plus a 2x. And then I'll get a minus 2x cubed from this right piece. So it looks like my 2x cubes are going to cancel out. And so this derivative is 2x over x squared plus 1 quantity squared. Now think about what we wanted to do once we found this slope. If we want a horizontal tangent line, that means we need a zero slope, and slopes are derivatives. So what we're going to do is we are going to force this derivative to be zero to find out when it happens. Now, since this derivative is a fraction, think about when is a fraction going to equal zero. You know that denominator never will because it's a quantity squared, and x squared plus 1 is never going to hit 0. So the only way this fraction can be 0 is when the numerator is 0. And when does 2x equal to 0? Well, if I divide by 2, then that's going to happen when x is 0. Now, depends on the question, and this one's actually a little bit vague, but usually they want to know the points at which you have a horizontal tangent line. So even though I've just found out what x is, that's not truly the point, because I would also need to know the y coordinate of the point. So how do you find the y coordinate of the point? Well, remember that y is the same as your function f of x. So if you ever want to know a y coordinate, you always want to go back to the original function right here. So we're going to let x be 0 and find out what that forces y to be. So if I substitute in 0 for x, I'm going to get 0 squared over 0 squared plus 1, and that's just 0 over 1 or 0. So the point at which I have a horizontal tangent line is just at 0, 0, or in other words, the origin. Okay? So if you ever want to know where horizontal tangent lines occur, take a derivative and set that derivative equal to 0 and solve for x, and then find the corresponding y. Alright, now that we've talked about the product and quotient rule, now let's move into higher order derivatives. Now the good news is if you know how to take a derivative using your shortcuts, then you know how to find higher order derivatives, because you're just going to keep taking a derivative over and over and over again. So first let's review a little bit of notation. We know that to find a derivative, usually we see that prime notation, like y prime if you're using y's and x's, or f prime of x if you're using x's and f of x's. That's equivalent to this notation over here of dy over dx, the derivative of y with respect to x, or the derivative of f with respect to x, or just df dx. And then you also will sometimes see this operator notation with this capital D with a little x and then the y inside. So this means the derivative of y with respect to x. So if I asked you to find a second derivative, you would first need to find the first derivative, and then you would just take the derivative again to get the second derivative. So the notation for that will now be y double prime or f double prime, or you would see d squared y over dx squared, or d squared f over dx squared, or this big D sub x with that square in there. Now if you look at this d squared y over dx squared, you may be wondering why the squares are kind of in a different position. So let me just show you where that comes about. You know that the first derivative of y with respect to x would look like that, dy over dx. So if I wanted the second derivative, then I would be taking the derivative of that with respect to x. And if you think about this just in a straight sort of variable way, the two d's are like a d squared, and then on the bottom I have two of these dx's, so both dx's get squared. So that's why the 2's are sort of offset and in different positions. That's where that comes about from. If you wanted a third derivative, you would have a triple prime or 3's. A fourth derivative, you would have a little 4 up there, a fourth prime, or little 4's. An nth derivative, you would have a little n where that prime should be, or little n's in these powers. So you can take higher order derivatives. You can take as many derivatives as you want to by just finding each derivative and then taking the derivative again to get the next highest one. Now in physics, there are some applications and meanings to these higher order derivatives, and we have talked about this a little bit. In physics, normally we see a lot of applications that deal with a position function, and usually we use the letter S to represent that position or that displacement, and it's usually a function of time. So position functions usually look like S of t. Now we've talked about this in the past. If you take one derivative of position, that gives you something called velocity. And in the case of a derivative, that's actually instantaneous velocity. Now something new would be to take the derivative again. So if you took two derivatives of position, that would be the derivative of velocity as well. And in physics, that has the application of representing something called acceleration. So one derivative of position is velocity, two derivatives of position represents acceleration. So that's something you want to memorize, that relationship. So let's practice finding some of these higher order derivatives. Suppose that our function f of x is secant of x. Let's find the second derivative of that. Now you can't find the second derivative without knowing the first derivative. So first we need to find f prime of x. So derivative of secant of x, this is one of those that you need to have memorized. Derivative of secant is secant tan. So this is going to be secant x times tangent of x. Now to find the second derivative, we're going to take the derivative of this answer, but you must be careful here. This is, again, one of these common mistakes that a lot of students make. There's implied multiplication between that secant times that tangent. So you do have to use a product rule to get your second derivative. You can't just take the derivative of the secant and then take the derivative of the tangent and multiply those two together. The product rule is more complicated than that. So to apply the product rule, this is our first, the secant x, this is our second. So we need the first times the derivative of the second. Derivative of tangent is secant squared. Then we need to add to that, or plus, the second times the derivative of the first. And the derivative of secant is secant tan. So secant x tan x. And then just cleaning this up a little bit, a secant x times a secant squared x is a secant cubed x. And then a tangent x times a secant x tan x. I'm going to put that secant x out front, and a tangent times a tangent is a tangent squared. So this will be secant x tangent squared x. And here is my simplified second derivative. Okay? Now take a look at number 16 here. If y prime is 2 minus 2 over x, find the fourth derivative of y with respect to x. That's what this means. We're looking for a fourth derivative. So notice that we already are given the first derivative. So if we take the derivative again, that's going to tell us y double prime, or the second derivative. Now before we can do that, you might want to rearrange or rewrite this function a little bit, because I have that x in the bottom. So what I'm going to do is move that x up into the numerator so that I can avoid my quotient rule. So this first derivative is actually the same as 2 minus 2x to the negative 1. So if I take a second derivative, this 2 will go to 0, and when I bring down my negative and multiply it by that minus 2 that's already there, it becomes a positive 2, and when I subtract 1 from the power, the new power becomes a minus 2. Now that's your second derivative, so if I take the derivative again, that'll be y triple prime, or my third derivative. Bring down the power times the 2 that's already there makes this a minus 4, and when I subtract 1 from the power, the new power becomes a minus 3. If I take the derivative again, that'll give me that fourth derivative, or d4y over dx4. So bring down the minus 3 times a minus 4 becomes a positive 12, and when I subtract 1 from the power, this becomes a minus 4. If you want, you can push that x to the fourth back down into the denominator, and there is our fourth derivative. Okay, we're going to finish up with a couple of applications related to these higher order derivatives. So suppose that we have an astronaut standing on the moon who throws a rock into the air. The height of the rock is given by S of t equals negative 27 tenths t squared plus 27t plus 6. S is measured in feet, so that's a height or a position, and time is measured in seconds, so that's a time. So this function they're giving us, this is our position function right here. So part A, find a velocity function. So what you need to recognize is that relationship, that velocity is one derivative of position. So I need to take one derivative of this. So if I take the derivative of negative 27 tenths t squared, the negative 27 tenths is going to stay there, and when I take the derivative of t squared, that becomes a 2t. And we'll simplify that in a minute. The derivative of 27t, that 27 stays there, and the derivative of t goes to 1, and then the 6 goes to 0 in the derivative because it's a constant. So simplifying, 2 divides into that 10 5 times, so this will be negative 27 fifths t plus 27, and that's your velocity function because that was one derivative. Okay? So now to find an acceleration function, you have to remember that acceleration is one derivative of velocity or two derivatives of position. Now we've already taken one derivative of position to get velocity right here. So I just need to take the derivative of this again to get the second derivative. So the derivative of negative 27 fifths t is just that negative 27 fifths because the t goes to 0 and 27 goes to 0 on the end. So our acceleration function is just negative 27 fifths. Question C. Find the time when the rock is at its highest. Now this is important. There's lots of ways to do this, but we want to do it using calculus. What we have is that this astronaut threw a rock up into the air, and then eventually gravity is going to pull it back down. So when is it at its maximum height? Right here. What you want to notice about calculus is that the tangent line at that peak has a slope of 0 because it's horizontal. So if you want to know when you're going to be at your highest point, that's going to occur when your derivative is 0. And one derivative of this position is velocity. So you are going to be at your maximum when your velocity, that first derivative, is 0. And we've already found that velocity function. So all we have to do is take that first derivative and find out when it's going to be 0. Find out when that slope is going to be 0. So if I subtract 27 over to the other side and then multiply by a reciprocal, multiply by negative 5 27ths, the 27ths and the negatives cancel out, so t is just 5. So in 5 seconds, that rock is at its highest point. Okay, and then the last question here is how does the acceleration of the rock compare with acceleration on Earth? Well, we know that on Earth, acceleration due to gravity is just that g. So the acceleration function on Earth is just g. And on Earth, if we consider direction, gravity is acting downwards, so usually that would be considered the negative direction. So what's g in our units here? We're talking feet and seconds. So on Earth, that g value is negative 32 feet per second squared. So that's what g is, or that's acceleration at any moment in time. So that's what happens on Earth. Let's talk about what happened on the moon. What was our acceleration function on the moon? Our acceleration function, a of t, was negative 27 over 5. And as a decimal, that's negative 5.4 feet per second squared. So it's not as strong as the acceleration on the Earth. It's not as big. It's still going in the negative direction, so minus, but 5.4 is much smaller than it is compared to that 32. So that's why you see those astronauts seemingly floating through the air, because the gravity isn't pulling them back down to the Earth as quickly as it does on Earth. Okay? All right, last example. Let S of t equal negative 16t squared plus 32t plus 48 represent the height of an object propelled from a cliff 48 feet high. So we have this big cliff that's 48 feet high, and we're propelling this object, and eventually gravity is pulling it down, and this is our position function. So the first question says, find the velocity and acceleration when t is 2. So if we want to find a velocity and acceleration, we better find the velocity function and the acceleration function first. So velocity, remember, that is one derivative of position. So if this is my position function right here, let's find the derivative of it. When I bring this 2 down and multiply it by negative 16, that becomes negative 32t. And then the derivative of 32t in the middle just becomes 32, and the 48 on the end goes to 0. So there's our velocity function. So what would be the velocity at 2 seconds? Well, we could just plug in 2 for t. And negative 32 times 2 is negative 64. And when I add 32 to that, I get negative 32 as well. And the units on this, because it's a velocity, should be feet per second. It should be a position over a time. So there's our velocity at time 2. Now let's find our acceleration. So to find acceleration, we need to take the derivative of velocity, which is the same as 2 derivatives of position. Well, here was velocity. Here was our first derivative. So the derivative of this again will be my second derivative, and the derivative of negative 32t is just negative 32, and the 32 on the end goes to 0. So there's my acceleration function. So what would be the acceleration at time 2? Notice that this acceleration function doesn't have a t left in it. And that's because acceleration due to gravity on Earth is always constant. It's always negative 32 feet per second squared, no matter what time you're looking at. The acceleration is constant. So this acceleration at time 2 will be negative 32 feet per second squared. That would also be the acceleration at time 3, at time 4, and so on. So there's that g that we were talking about a moment ago. Okay, the next question. Find when the object reaches its maximum height. So again, we want to know when this peak is going to happen. And as we talked about earlier, that is going to occur when your derivative, because that's the slope of your tangent line, is 0. So in the context of position and velocity and acceleration, the derivative is velocity. So we need to find out when that velocity is 0. So our velocity function was negative 32t plus 32. So let's find when the velocity is 0 by setting negative 32t plus 32 equal to 0. So if I subtract 32 and divide by negative 32, we get t is 1 second. So after 1 second, it's at its peak. The last question here was, what is the maximum height? So how tall does this object actually get? Well, notice that this height right here, that's exactly what a position is. That's your S. You're not going to use V, you're not going to use A, you're going to use the original function S of t. So anytime you want to know an actual height, you want to use the position function, the original one. And we want that height at that peak, which was happening at 1 second. So what's your height at 1 second? Well, that's going to be whatever S of 1 is. And our position function was negative 16t squared. So we would want negative 16 times 1 squared plus 32 times t plus 48. So 32 times 1 plus 48. So I'm just plugging in 1 for that t. And 1 squared is 1 times negative 16 stays negative 16. So we get 16 plus 48, which is 64. And remember, this is a height, so my units should be 64 feet. So that's your maximum height reached by your object. Okay, that concludes our lecture on the product and quotient rules and higher order derivatives. There are several new rules that you want to have memorized, as well as memorizing those tangent, cotangent, secant, and cosecant derivatives as well. Good luck.